In the last video, when I introduced alternate bases for a number system, and in particular binary, all of the examples I used involved positive numbers. But because everything on a digital computer needs to be represented in terms of ones and zeros, we need a way of representing positive and negative numbers without the presence or absence of a minus sign. A first thing we might think to try is to designate one bit out of our number to represent plus or minus. So for the first bit, we could use 1 to indicate the presence, or 0 to indicate the absence of a minus sign. For this to work, we would need to know which position in the number represents the potential minus sign, and which positions represent ordinary digits. And so this inspires the idea of a fixed width number, that we will pick a number of bits that we will use to represent our values, like 16 or 32 or 64, and we will always know that the first bit out of that set corresponds to the sign. This approach would work and is known as the signed magnitude representation, but it's not the way that modern computers represent signed integers. The representation that is actually used in practice is known as the 2's complement representation, and the way it works is to use the leading digit not just as a potential minus sign, but to in fact use the leading digit like the other columns of the number where it represents a power of 2, but where all of the other columns represent positive powers of 2, the first digit will represent a negative power of 2. So, why is this a better idea than signed magnitude? Well, for one thing, it avoids the problem of having a duplicate number where we would have both plus and minus 0 represented in our number system. But much more importantly, using every bit of our representation, that is, every column of the binary number, to represent some power of 2 makes implementing the circuitry that does arithmetic on those integers much, much simpler. We will see next class, when we talk about binary arithmetic, that the same approach can be used to perform addition and subtraction on both signed and unsigned numbers, specifically because of the 2's complement representation. As with the signed magnitude representation, in 2's complement there is one column out of our number that has a special purpose. Rather than meaning some positive power of 2, it means a negative power of 2. And so, in order for us to know which column is the special one, we need to know the bit width of our number. The standard bit widths that exist in C data types on a modern computer range from 8 to 64 bits to represent an integer, but it is also possible to have integers with a different amount of bits, and this will definitely come up in some of the examples that we will work in class and on quizzes, because we don't want to always have 8-bit integers, and going all the way to 16 or 32 would be really tedious to do by hand. So to illustrate the concept, let's start by thinking about a 4-bit integer. For an unsigned number, all of the columns behave exactly as we saw last time when thinking only about positive numbers. An unsigned integer represents only positive numbers, and so all of the columns behave exactly as we saw in the last lecture video. We'll have a 1's column, a 2's column, a 4's column, and an 8's column, and so 1001 would represent the integer 9. On the other hand, in a signed 4-bit integer, where we're using 2's complement, now the leading digit represents a negative power of 2. So we have -8, 4, 2, 1, as our columns, and so we have 1, -8, no 4s, no 2s, and 1, 1. And so this is the representation of -7 in a signed 4-bit integer. So to hammer the point home, in an unsigned integer, the leftmost column behaves like any other column. It's just a bigger power of 2. So here, when we have 4 bits, the leftmost column is representing 2 to the third. So this is the column for 2 to the n minus 1. Whereas in a signed number, the leftmost column is representing minus that power. And so here, this is the number of negative 2 to the n minus 1s in our number. To give another example, if we use an 8-bit signed integer, now the columns of our number represent 1s, 2s, 4s, 8, 16, 32, 64, and negative 128. And so this value is equal to minus 128 plus 64 plus 4 plus 2. And so this is negative 128 plus 70 is equal to negative 58. So for whatever fixed bit width we are working with to represent our signed integers, the rightmost n-1 columns will behave exactly as they do for unsigned integers, but the most significant bit represents the presence or absence of a large negative power of 2. Once again, in defining how the number system works, I've shown you how to convert from the new number system to base 10. So we can convert from a 2's complement signed integer to a decimal integer in our normal notation. But we should now talk about how to convert from decimal to 2's complement. Converting to 2's complement, if we have a positive number, is almost identical to what we did converting to ordinary binary. The only thing that's different is we now have a fixed bit width, and so we would need to check that the decimal number that we are converting fits within the number of bits that we have available in binary. But as long as there is enough room in our fixed number of binary digits, we can do exactly the same conversion that we did before. So what we're really talking about here is how to convert a negative number in decimal to a 2's complement representation of that negative number. And broadly speaking, we have two approaches. One of which is to build the negative number directly, and the other of which is to build a positive number and then turn it into a negative number. Since we're representing a negative number, we need a negative power of 2, and since there's only one option for a negative power of 2, we go ahead and start by putting a 1 in the leftmost column to give us a negative starting value. And now that we've begun with a large negative power of 2, all the rest of the columns that we'll be filling in will be representing a positive number. And so we can figure out the difference between that negative power of 2 and the number that we want to represent. That will be a positive number, and we put that positive number into the remaining digits of our 2's complement representation. And now we can take our pick of the top-down or bottom-up methods for coming up with the representation of a positive number in binary and use that in order to fill in the difference between our large negative power of 2 and the number we actually want to represent. As an example, let's figure out how to represent -85 using an 8-bit signed integer, known in C as a char. Since we're using an 8-bit number, we start by filling in -2 to the 7th. And so -2 to the 7th is -128. And so now we can take the difference between -128 and -85. That difference is 43, and so we know that we want the remainder of these digits to represent the number +43 in 7 bits of unsigned binary, so that when we add it to the -128 that we've already included, we will be representing -85. We can now use either top-down or bottom-up to come up with our representation for 43. Let's do it top-down. So there are no 64s. There's 132. No 16s, but there is an 8. No 4s, but there is a 2 and a 1. And so now we have a representation of -85 as an 8-bit signed integer. The second alternative available to us is to instead build the number 85 and then convert it to -85. And this is because converting between positive and negative numbers in 2's complement is relatively straightforward. In 2's complement, the way to convert between -n and n, whether n is a positive or negative number, is to flip all of the bits and add 1. One way to think about why this is that the number 0 is represented as all zeros, whereas the number -1 is represented as all ones. And so we can think of the number of zeros that we add as counting down from -1 by taking away positive powers of 2 on a negative number, just like adding 1s to all zeros is counting up from 0 on a positive number. And so if we flip all of the bits, it's like we counted down from -1 instead of counting up from 0. And so, to go from n to -n, we can flip all of the bits and then add 1, and we will have been counting down from 0. So if we start by representing +85 in 8-bit binary, we'll have no 128s, we'll have 1 64, remainder is 21, so we'll have no 32s, 1 16, that gives us a 5. We'll have no 8s, we'll have a 4, and then no 2s and a 1. Now we flip all of the bits, so all of the 1s become 0s and 0s become 1s. And now we add 1, and that gives us our representation of -85. Of note, it's possible that adding 1 would force us to carry, and we would do that in a manner akin to grade school addition, where if we get 1 and 1, we will carry the 1 and put a 0 below. We'll talk much more about doing addition in binary for next class. In the last video, we saw that we could multiply a binary number by 2 by shifting all of its digits 1 to the left, and we could divide by 2 by shifting all of the digits 1 to the right. But when we did that, we weren't yet using the 2's complement representation, which meant everything was positive and we didn't have a fixed bit width. So, what does it look like to multiply or divide by 2 when we're using a fixed width 2's complement number? If we have a negative number, like -6 in 8-bit 2's complement, we can multiply it by 2 in much the same way that we did with positive numbers. If we shift everything to the left, well now, since we have a fixed bit width, one of our digits will fall off the left end of the number. And so we'll be left with those 7 digits, and we'll fill in a 0 from the right-hand side, just as we did with positive numbers. And now we're left with minus 127 plus 64 plus 32 plus 16 plus 4, and that, if we were to write it all down and work it out, is minus 12. The easier way to think about that is all ones would be minus 1, so let's subtract a 1, a 2, and an 8. So we're subtracting 11 from minus 1, and that's minus 12. So a left shift, where we fill in a 0 on the right-hand side, multiplies by 2, just like it did with positive numbers. There can be problems when we're multiplying by 2 in a case such as this one. If we had all ones, we'd have minus 1, and now we subtract 64, so this is negative 65. And now if we were to shift this to the left, we would get, which is a positive number. This is, in fact, plus 127. So if we're doubling a number by shifting to the left, and doing that changes the sign either from negative to positive or positive to negative, then we know that the answer was wrong. But it turns out that this is exactly the case where it's not possible to represent the number we were going for with our fixed bit width. In particular, 2 times negative 65 would be negative 130, and the smallest number that we could represent in 8-bit 2's complement is negative 128. And so the reason that we couldn't do this is simply because the number we were trying to represent is too large in magnitude to fit in an 8-bit signed number. So what about doing division by shifting to the right? If we start with our representation of negative 12 and shift everything to the right, like we did last time, we'll get a positive number as the result. We got a positive number when we tried to divide a negative number by 2, so that's definitely wrong. But why was it wrong? Well, the only problem here was that we started with a negative number, and when we shifted, we filled in a 0 for the sign bit, which turned it into a positive number. If we had instead filled in that sign with a 1, we would get minus 6. So by filling in a 1 for the sign bit when we shift a negative number to the right, we ensure that it stays negative, and we succeed in dividing by 2.